detected in the Martian atmosphere and how that was done?
Yes. Shall I feel that? Okay. We started our detailed campaign at the NASA Infrared Telescope facility in Mauna Kea in 1999, just taking some snapshots of Mars to assess signal levels and so on. We got really going strongly in 2001 with a few nights devoted to the search. But in 2003, in January, we made our first detections of methane. We then expanded that in March of 2003 using basically detected the material that you saw today in these videos and reported that at the DPS meeting in October of 2003 we reported it as a sensitive search for methane, but we showed the actual spectral lines and the detections. So we actually knew that we had methane as early as late 2003, but since then we have spent a great deal of effort honing the analytical procedures and beginning to remove instrumental artifacts down to second and third order effects to really present the material in a way that was unambiguous and unassailable from any point of view.
I would also like to point out that Mars Express measured methane in the atmosphere, but because of the nature of the instrument, they're unable to find variability on latitudinal or seasonal basis. So in other words, you have to average over such a large amount of time that you could tell that methane was there, but you couldn't tell that it varied.
And Mark, do you have a follow-up?
I do. It's basically to ask what you need to do next beyond further remote observations from the Earth using the telescopes you're using. What would you do in orbit or on the surface of Mars to pursue this?
Well, one of the things I can add is that the Mars Science Laboratory has, as part of the SAM instrument, which is Sample Analysis at Mars, which is a gas chromatograph, mass spectrometer, also has what's called a tunable laser spectrometer. And it can measure methane down to sort of the 100 parts per trillion level. And with that on the surface of Mars, it can tell whether or not there's any methane there at all and also any variability. In addition, SAM has the capability to concentrate gases, and so what that can do is improve the measurement capability by another 2 orders of magnitude. So with the Mars Science Laboratory on the surface, we'll be able to tell whether or not there's methane and follow its variability on a very short timescale basis.
Could I add to that?
Yeah, please.
And what Michael just described also allows us to measure the isotopes of carbon, which is, I think, where you were driving at.
Okay, we're going to go to the phone lines now, and for the panelists, whoever answers a question, I'm not quite sure if the media can see you, so if you can identify yourself when you answer the question. So we're going to go to the phone lines, and I believe we have the Associated Press. Seth, do you read me?
Yes, I do. Can you hear me?
Yes, go ahead.
Yeah, this is Seth. This is Seth Bornstein at the Associated Press. For Mike Meyer, and then I have a follow-up. Mike, just last month, I believe, Mars Science Lab narrowed the landing sites down to 4 and eliminated Nili Fosse as one of them. This sort of makes Nili Fosse a little more interesting, and you still have time, a little extra time. And since you don't have another lander going until 2016, how is NASA Mars program going to respond to this in terms of changing where you're looking next when you go to Mars?
Well, certainly what happened in the landing site process is we had 5 top candidates, of which Nili Fosse was one of them. And as we're getting down to the wire, Nili Fosse is at the highest altitude and pretty much at the envelope of the MSL capabilities, particularly with what we know of the capabilities now, because there's still things to be tested. And that's why, basically in the interest of time, we narrowed it down to 4 sites. And you're right, we now have 2 more years to look at this. We certainly have our top candidate sites, and adding more potential landing sites is certainly within the cards. And also we'll have a better idea of what really is the landing capability, the EDL capabilities of MSL. So Nili Fosse is not ruled out. We kind of reset the clock for another 2 years in terms of determining what the best place is to go on Mars.
Our next question is from USA Today, Dan Vagano. Do you read me?
Yep, very good. I was wondering, sort of following up on Seth's question, how far down would a sample return mission have to dig to get at this stuff you're talking about today to figure out the answer to this?
Shall I answer that?
Yeah, and then Lisa.
Or Lisa, you want to take it?
Well, I think if we're talking about a subsurface ecosystem that would be analogous to what we see on Mars, we would have to go down probably, at the very least, several meters. We'd need to get away from these aggressive oxidants that are in the surface, and we'd have to get down to a zone where at least seasonally there was some sort of liquid water. So I think a very shallow drill is unlikely to yield compelling evidence because it looks like this planet erases the kind of evidence you'd want to see. If we get deeper, it still may be quite a challenging detection because these levels of methane indicate that the amount of biomass might be at most a very thin, nearly invisible film spread over the surfaces of fractured materials. Mike?
Right. I'd like to add to that a little bit depends on whether it's a surface environment, as Lisa was commenting, or material that's emerging from below the permafrost. If that's true, then probably we're talking depths below the plane surface of maybe several kilometers, and you'd only see the effluent material at scarp faces, canyon walls, crater walls, and so on, where pores can open seasonally and release the pent-up gases. So to sample that material, that would require a different technology and so on. So there are different scenarios that we have to think about before we can really design the strategy properly.
Even on Earth, when we're trying to look at life that's in these deep subsurface brines, we have to filter hundreds of thousands of liters of water to concentrate enough biomass to really be able to characterize it, to have any chance of culturing it. So we're talking about a very aggressive campaign to make an equivalent exploration of these deep brines on Mars.
Our next question is from Sky and Telescope, Kelly Beatty.
Thanks very much. I think this is for Dr. Atreya and Dr. Mumma. Dr. Atreya, you mentioned that the likely contribution from comets and asteroids was less than 1% and not consistent with what you see there. Why is that? I mean, how large a comet would you need, because comets have some methane in them, how large a comet would you need to strike to generate this amount of methane, and is the shape of the plume consistent with that?
Yes, that's a good question. So one cannot really rule out the possibility that comet could have struck Mars recently, but the size of the comet that we're talking about is several kilometers in size, and that should have struck Mars in the past few hundred years at most to be able to produce the amount of methane that Mike's and Geronimo's observations are showing here. And if that kind of a impact took place, we would have known it from the observations of Mars we have from the orbiters. The other thing that we want to keep in mind is that any contribution from the comet is going to be homogenized quite quickly, but that would also apply to other sources as well. So that was, and there was another part to your question, I think. Did we lose Kelly?
Kelly, can you repeat the other part? Okay, I believe he signed off. Let's now go to Discovery Channel. Irene.
My question is for Ms. Pratt. I wanted to know if you think that there is enough information about what might be on Mars to actually change the philosophy that NASA has been going about its Mars exploration program as far as searching for signs of water. I was a little struck by your closing comment about how it's a prudent and the right time to start looking for life forms on Mars.
Well, I certainly think it's important that we are always reevaluating our exploration strategy with new information, and this is certainly a very important new piece of information. And as I said, it's not only important because it could be, you know, the exhaled breath of a microbial ecosystem. It also presents the possibility that it's a consumable substrate for microbes. So either way, I think